say?
I just started the recording.
Okay, so the Cognitive Network Special Interest Group was founded, I think, almost 2013 or so, and I am the founding chair of that special interest group. Our current vice chairs are Dola Saha, who you can see here from SUNY Albany, and Charles Clancy from MITRE. So you can discover more about our group in this SecIG link here on LinkedIn. You can also search it using that search term, IEEE Cognitive Network Security Special Interest Group on LinkedIn. If you would like to join, get to know more about what we do, you can either email Dola or me. My address is here. Currently, we have about 201 members. The virtual seminar series started in November 17th. The idea here is to get eminent people in our research area to talk about security issues as it relates to cognitive radio networks, 5G, 6G, and so on. Our inaugural lecture was by Professor Winspur on November 17th. We had 270 registrants and about 105 attendees. He spoke about physical layer security in wireless networks. Today we'll have Professor Kaushik Chowdhury, who I'll introduce in a minute, and he'll be talking about deep CNN for device identification. And the pipeline is Professor Rosehu, Wade Trapp, and Narayan Mandayam. And if you need to get access to our recorded talks, you can email either of us. And then I'll just go quickly to introduce Professor Kaushik Chowdhury. He is a professor and a faculty fellow in the EC department and an associate director at the Institute for the Wireless IoT at Northeastern University, Boston. He was awarded the PKS Award in 2017, the DARPA Young Faculty Award in 2017, ONR Research Director Director of Research Early Career Award in 2016, and the NSF Career in 2015. He has received numerous Best Paper Awards at several flagship conferences, including Infocom, Globecom, ICC, and so on. He is presently a co-director of the Powers platform, which is an NSF effort, and the Coliseum RF emulator. His current research interests are in machine learning, applied to wireless systems, network robotics, wireless charging, and at-scale experimentation for emerging 5G and beyond. So with that intro, I will stop my slide share and give the floor over to Professor Kaushik. But before I go away, if you have questions about Professor Kaushik's talk for him, please use the chat box to type in your chat. We will read these questions out at the end of the talk, and Professor Kaushik will answer them. Thank you.
Thank you, everyone. And if I may be allowed to share my screen, that would be.
Okay, I thought I had made you co-host. Let me do that quickly. Sorry about that delay. Okay.
Perfect.
You should be able to do it now.
Yes, excellent. Thank you. All right. Okay, so thank you, everyone. Thank you, Dola. Thank you, Subha, for inviting me to this exciting seminar series. And I'm very excited to be part of this exciting SIG. This is an important work that is happening, and we are really at the point in time where the work of this SIG is going to make a lot of difference. I'm very excited to be here. So so today I want to talk to you about a series of works that we've been doing on device identification. Essentially, we are trying to identify a device based on its transmitted signals only. And there are a number of different security aspects and applications, and I'll talk about a few of them today in this talk. So I'll try to keep this at a high enough level for us to get a good flavor of it, but I'll also point you to some of the papers that we have drawn some of these ideas from for more deeper investigations. So I'm honored to be supported by DARPA, NSF, and ONR, and lucky to be collaborating with a number of outstanding individuals, Stratis, Tommaso, Jennifer, and this is a collaborative work with all of us. All right, so let's get started. And really, I'd like to first give credit to my team. These are the giants on whose shoulders I stand, and the particular work that I'm going to present today is by these individuals who have boxed in blue circles. They are really the leading the work here. I'm mostly a cheerleader on the side, egging them on, but they are really the key players in this game. So what problem are we talking about today? If you think about the way wireless networks are going, you're going to see an ubiquitous spread of access points, of mobile devices, and they're going to be everywhere. So imagine a scenario where there's a dense deployment of access points and dense deployment of users of these access points, right? And so if you're like me, imagine that you're always running last minute, and you just have this little amount of time to quickly access or connect your device to the nearest access point, upload your data, and then rush. You have to make it before the door closes of this train, right? So it's all going to be on a very short time scale. So, for example, in this scenario, there is a number of Wi-Fi access points all around, and this makes sense given the incredible investment that is happening in ubiquitous deployment of these Wi-Fi devices. Now, here's a nice lady who wants to connect to the access point at the roof of this busy subway station. Now, while her device is connecting to this access point, what happens if there is a malicious entity who also has a device which is trying to impersonate that legitimate access point? And by impersonating that legitimate access point, is able to draw traffic from the legitimate user to itself, thereby creating a sort of a security risk and perhaps even eavesdropping on confidential information. So could it be possible that this device that this lady is carrying is able to detect a device purely by its RF signals without even going up the layers of the protocol stack for other more enhanced security mechanisms? So can we do this at the physical layer itself? And that's going to be the premise of this talk, where we are trying to propose a vision that indeed it is possible. Indeed, each device has a unique characteristic which imparts those characteristics onto the signal. And if we learn those characteristics of those transmitted signals, we will know who is the device. So that's going to be the hypothesis. So how do we do this? So the method is broadly described as RF fingerprinting. And the message here is that you want to detect these fingerprints or these characteristic signatures inside a radio's electromagnetic transmitted signal. Now, if you look at these three devices on the left, and they are all transmitting to this one receiver. Now, if there is this one transmitter, which is going to have a unique characteristic in its transmitted signals, where are those characteristics coming from? So let's dive into this device. Let's open it up and see what's inside. So if you go further and deeper into its processing chain, you find that this is a very regular processing chain, right? So you have the digital baseband, you have the digital to analog converter, the filters, and then you go to the mixers and the local oscillator, in which case you generate an in-phase and a quadrature phase signal. So that's what you see. So here's the in-phase, and here's the shifted phase, and these becomes the I and the Q samples. Now, if there is a mismatch in the way the gains are applied to these two signal phases, you immediately have an IQ imbalance. So this is one example of a characteristic signature that is imparted into the transmitted signal if there is a mismatch in these two IQ paths. Now, how does that manifest itself in the signal that is transmitted? So if you look at a 16-QAM constellation diagram, and you see in-phase and quadrature amplitude points, the reference points, or that means the legitimate points of the constellation, are shown by the red dots, and the shifted ones, because of this unequal gain, is shown by the plus. So as you see that the plus is slightly shifted, and if these shifts are unique to a device, then this is a signature that is imparted by the device onto the transmitted signal. Now, there are a number of other signatures that we can apply. For example, we can have phase noise, we can have nonlinear power amplifier distortion. And each of these, as you see, is either rotating the constellation or stretching the constellation or compressing the constellation. And all of these cumulatively give you one signature. And that is what we want to detect. Now, the difficulty here is that we may not exactly know what is the source of this unique distortion. And if we don't know this, then we have to rely on deep learning techniques where we are not really doing feature-based engineering. We are simply letting the architecture learn what the signatures are. Now, so there are two ways in which we can approach this problem. The first approach is we simply design interesting pre-processing steps and deep learning architectures that will take in these raw IQ samples and will process them in some interesting ways. And I'll talk to you about partial equalization in a bit, but they'll process these raw IQ samples and will be able to predict what device is transmitting. There's another approach in which I can have feedback from the receiver going back to the transmitter. In this case, the receiver is going to tell the transmitter that, look, if you distort your transmitted signals in this little manner, then you will become a lot more differentiable to me than before. So we can use just a straight line path, or we can also use a feedback path. And these are the two broad categories of works that I'll talk to you about today. And each, of course, has pros and cons. All right, so let's go a little bit deeper into what architectures are we going to use, and at a high level, how are we going to do this classification? So we are going to take architectures, we're going to borrow them from the machine learning community. So the baseline is adopted from what we call is the AlexNet, and the other one we use is the ResNet. And both have been phenomenally successful in various image processing tasks. The ResNet has, on what you see on the right, has what you see these skip connections, and these skip connections help in minimizing the gradient loss as it propagates along the back propagation path. So what happens is, if you have a very deep architecture, it is possible that the gradient diminishes as you go layer by layer in the back propagation. By the skip connections, the gradient can jump across these layers, and you still can train a deep network. So we've adopted these, but one thing what we have done is these were all designed for images and would take in two-dimensional inputs. So we had to convert these into one-dimensional inputs, and so that we can give them a vector of I's of the Q samples. So let's look at the baseline first, and on the left-hand side. And while this appears to have fewer layers, and it is true it has fewer layers, the number of parameters that we need to train is far more here than ResNet. So let's go a little bit deeper into the way in which we are giving the inputs, right? Because ultimately we are operating with IQ samples. So here is the definitions, and I'll keep using them multiple times. So I just want to outline them to you up front. So the first thing is a device. A device is the target of the classification. We want to predict that this is the device. Now, each device is going to transmit a series of IQ samples. So one such sample is a pair of I and the Q components of the IQ sample pair. Now, what I can do also is that I can take a device, I can switch it on and switch it off. And when I've switched it on, it generates a number of IQ samples, and I'm going to group them together and call it as one example. So an example is nothing other than a series of IQ samples grouped together, and I can switch on and off the device. As you can see here, I've switched on and off capital K times to generate K examples from the same device I. Now, each example, I'm going to take that example, and I'm going to slide a window across that example. So I'm going to take one of these files here, I'm going to stretch it out in a vector, and I'm going to move this window slowly across. And each time I move the window, I'm generating a new slice. So for example, in the first position of the window, I have the first slice of j samples. Then I move the window one position on the right, and I have 2 to j plus 1, again j samples, and so on. So these are slices, and I'm going to train my network and test my network on these slices. And this will become a little bit more clear as I go in the way in which I'm computing the output. So if I go to the output, right, the final output of the classifier, this is nothing other than a vector again, and this vector has n is a vector of size n, and n because I have n classes or n devices that I want to identify. Now, each such output is essentially a probability, and the probability simply says that given the jth slice, with so and so probability, the jth slice comes from the ith device, or in this case, the second device or the nth device, or so on. So this is nothing other than the probability that this jth slice comes from the n device, and this is nothing but the jth slice comes from the second device, and so on. So to come up with a final prediction of this entire architecture, I'm simply going to take the maximum of whatever is the maximum probability, and that's only going to be for one slice, right? And I'm going to essentially do a majority vote of all the slices that compose an example. So if I have 100 slices, I'm going to check all those 100 slices and see how often is one slice predicted as coming from device 2, and I do that by looking at the maximum value of this probability vector for that slice. All right, so that's the way I'm computing a final decision on who is transmitting. So I take that, right, and this is a per slice accuracy. I convert it into a per example accuracy by taking the majority of all slices, and that becomes the final decision. So I'm going to be interested in an example accuracy, okay? Now, if I go further, I want to tell you that if I just simply apply these architectures as is on IQ samples, it's not going to do very well. And I'll show you later on why. But I also want to say that there are 3 tricks that I'm going to use to make it a little bit better. So the first trick that I'm going to use is called as partial equalization. And what we are doing here is that if you look at these two plots on the left and the right, on the left is what you see, the IQ samples that you get after the signal has passed through the channel. Now, this is originally a QPSK waveform, but imagine what sort of distortion and that is being added to this to the received signals. Is you really don't see these constellation points clearly. So one thing what we need to do is we need to compensate for the channel without affecting the transmitter's own distortions, which I want to recognize. So that's what we call is as partial equalization. And what we do here is that we reintroduce frequency offsets, which are more unique characteristic about the transmitter, but we take out the channel-induced distortions. And once you get that, a slightly pre-processed signal, we use that for training. And that does help in increasing the accuracy of the classification. Now, this can only work if you know what kind of waveform you're transmitting. So if you know this is going to be Wi-Fi, you can do this. And if you don't know this, then you can't do this, this sort of a partial equalization. And I'll show you what happens if you just use raw IQ samples. Okay, so this is one trick that we use, but you have to know the waveform type. All right, so let's go further into the next step. The next step is called data augmentation. And here we have taken techniques that have worked well for the image processing community, where let's say you have an image and you rotate the image, or you change the lighting of the image. You create blurring or pixelations in certain points of the image, and you use that to increase your training set. In our example, since we're dealing with RF, we take in these IQ samples, we normalize them, and during training, so imagine that I have a number of slices, right? And the slices are composed the same way as I showed you earlier. Taking an example, moving a window, each time a window moves, I get a slice. So here are a bunch of these slices. Now I'm going to take each slice and I'm going to distort them. How am I going to distort it? I'm going to design a complex filter, and the coefficients of this filter I'm going to draw from a Gaussian distribution. So I'm not really adding variations specific to a certain wireless channel. I'm mainly adding noise. So this is an open area of research as to how do you design channel-specific augmentations. We have not done that, and it's an open area of research. So, but what we do here is that we take in the slice, we distort it using the Gaussian, the filter from using coefficient from a Gaussian, and the Gaussian itself can have a number of different mean and variances, and that depends on the kind of data and the distribution of the data that you're using. So we take in these. Now, each time you're going to distort this particular slice, you're going to create a bunch of these distorted slices. So imagine that you're multiplying your data set, right? And you're creating a bunch of these distorted slices, which you're using for training. Now, when you're using for testing, you're doing something same. You're taking all these slices one by one, as you would in a regular test scenario. And then again, you are passing them through the same FIR filter that you are drawing from the Gaussian, and you are creating multiple distorted versions of the test set. So your test set is also expanding. Now, the way we solve this, the way we compute the final accuracy is the same way as we did before. Each of these slices is passed through the classifier, and out comes a probability vector, which tells you with some probability that this particular distorted slice comes from a device. And you take the maximum of these for that particular slice, and then you move it through all the slices that compose examples. So it's exactly the same way. The only thing that's changing here is I am introducing more noise, and this noise is helping the classifier to generalize and be a little bit more receptive to situations and conditions that we have not exactly seen in the measured training set. All right, so that is step number or trick number 2. And trick number 3 is we take in a packet, and the first thing we recognize is that the payload has a number of different modulation schemes. So we don't take the payload right now, we only take the preamble. And the preamble generally has a very simple modulation scheme, generally BPSK. So we take this, just a preamble piece of it, right? And we separate the payload and the preamble. We take the preamble and we pass it through what we call is as an attention network. And I'll tell you a little bit more about how this all works, but we are using this preamble to learn a compensation for the channel without knowing or without actually doing a partial equalization step. So I'm just simply extracting the preamble out and trying to learn the channel and compensate for the channel. And the way we do this is that we take the original classifier as an initial starting point. We train this without without this attention network that you saw at the bottom. And then after that, we do this split, we attach this attention network, and we retrain the whole thing again. And what we see here is that this output is nothing other than an 11/2 tap output, and this is sort of convolving back into the signal. And thereby, the intent is that we are removing the effect of this channel by learning this compensation filter and giving a clean signal for training. So that is the other piece, the third trick. Now, do these tricks work? So let's just see how we do this. Now, as part of the DARPA program that I was leading, we were given a number of signals from Wi-Fi and ADS-B or plane tracking signals. Now, we separated them into training, validation, testing. And let's just see how it works for a sample set of 100 devices. So we have 100 Wi-Fi devices. And my goal here is to tell you with what accuracy can I say that this one example comes from a certain device. Now, example, remember, is simply on-off, right? It's going to be a very short set of IQ samples. Okay, so if I take one example, and if I simply run without any of my tricks that I had, if I simply run ResNet, I get about 64% accuracy. So not too much, not too great, right? So I can definitely do better on this. So one way I can do things better is if I group a number of consecutive examples together. And information theoretically, this is a simpler problem than identifying one example in isolation. So in this situation, I just have to say that I have received 3 consecutive examples. All 3 must belong to the same device, which device it is. If I do that, I call this as multi-burst. I can push this up to 99% accuracy. But my interest is still up on a per example basis. I still want to push the envelope of this one example. So how well do I do there, right? So if I use all my tricks, if I use data augmentation, the attention network, and learn the channel, if I do this partial equalization, and if I use this deep enough 1D architecture of ResNet, I can push this up to 85%. So this is significantly better than the 64% you saw earlier. But still, what is the catch, right? The catch is that all of these were done using training and testing data sets that were collected at about the same time. Now, if I do this, if I train on a data set collected on day 1, and if I test this on a data set collected on a different day, look at how the accuracy falls to about close to 50%. So that means I'm still being affected by the channel. So I want to do something better. I want to change this in a way that I can be more channel resilient. So what are the 2 ways to do this? And this is where it comes in, where I'm going to use some feedback from the receiver to the transmitter. So the first way is we will add impairments. By adding impairments, it's like me telling someone that go take this identity and suppress your inherent, your natural identity. I'm going to force an impairment down to you, and you will behave like a device. And if I design my impairments in such a way, then you are going to be differentiable, more differentiable than you were before. So there's a feedback loop where the receiver is telling the transmitters, go use these impairments of a certain level. So the main contribution of this particular work is how do you identify what are the impairments and how much should you add in it? And there's a trade-off here. You add more impairments, you will not be able to decode the data because of this increased distortion level. You add less impairments, you will not be differentiable enough. So that's the fine line we need to walk on. All right, so let's understand a little bit more about what these impairments are going to be and what are the other challenges. And so what happens if someone overhears these impairments, right? And then can they just adopt these impairments and become a device? There's a risk of that. So how do we overcome that? All right, so there are a number of different impairments, as you can see in our software-defined radio. We're going to focus on DC offsets and IQ imbalance. All right, now the DC offset is nothing other than a DC value at the 0 frequency mark. And this is easily compensated and generally compensated before you start your transmissions. Now, the IQ imbalance is interesting. The IQ imbalance is interesting because if you have this difference in gain in the I and the Q phases, what you actually see is a signal component in the image frequency of the actual frequency that you want to transmit. So you want to transmit this at this FLO, but you see an image at minus FLO. And ideally, you want to suppress this one. But what we want to do is we don't want to suppress it, or we want to suppress it in deterministic ways so that this impairment is there, but in a way that makes the signal differentiable without distorting the signal too much that it can't decode it. All right, so so let's go a little bit deeper into this whole IQ imbalance thing. Now, on your right-hand side, you see the actual desired RF signal. And on the left-hand side, you see that image frequency that I was talking about. right? And if you leave aside all this math, this difference between the level of the wanted signal and this level of this image frequency signal, this difference is called as the image rejection ratio. Now, what I can do is this. I can use the knobs that I know in new radio, and these are these certain tools by which you can set. These are complex numbers that you allocate using these tools, which changes the image rejection ratio. So with a certain correction factor, if you insert this complex number, you get a certain image rejection ratio. You insert a different correction factor, this image rejection ratio changes. So I want to insert these correction factors in a way that leaves a little bit of this a finite image rejection ratio, does not completely move this down to 0 here, and still is able to make it a little bit more differentiable. All right. So the goal here is, does this work? And what do I mean when I say that impart an identity onto someone? So here are some scenarios where, imagine if I take two radios, R1 and R2, right? And I'm going to connect it to a receiver using a cable, or I'm just going to keep an over-the-air channel. So in the first series, or the first row, I'm only going to take a single radio R1, and I'm going to connect it to the receiver using a cable, or I'm also going to use over-the-air channel. So what I'm saying here is that no matter whether you use air or the cable channel, if you allocate these impairments, if you see this is IQ level 1, IQ impairment level 2, IQ impairment level 3, as you inject these different impairment levels, the constellation of what you receive at the receiver is exactly overlapping, irrespective of the channel. That means I can remove the effect of the channel by forcing an identity introduced by this particular level of this IQ sample. Similarly here, I can take two different radios, give them the same impairment, and they behave exactly similar. So this is really the motivation that says that let me find these impairments, let me train on them offline, and then in real time, I will just inject the impairment onto the radio, and they will become a radio that I've already pre-trained on. So that's really the takeaway idea here. Now, so the question is, how much of these impairments should I add? And what is the methodical way of adding this? So obviously, we are going to balance between adding impairments for differentiability and increasing the bit error rate at the receiver. These are going to be the two, or each one trades off with the other. So I'm going to adopt a metric called as the Earth mover distance. And this is nothing other than sort of mapping each point of a constellation as it moves. As I add more impairments, as you see, this constellation becomes more distorted. So how much is this displacement that has happened of each of these points, and take the minimum of the absolute value of this displacement and basically sum them up over all the points of these two sets. So that's really the Earth mover distance. And as you see, as I increase impairments, this Earth mover distance also changes, this value changes. So I'm going to keep this Earth mover distance less than 0.1, and that is going to determine what is the maximum impairment level am I allowed to add. So I take all of this and I simply arrange them in an order. I can jumble them up, right? And I can create permutations. I can group them in twos. And when I group them in twos, there's something interesting thing I can do. For example, look at this tuple. I can transmit, whenever I transmit a binary 0, I can use this impairment, I1. Whenever I transmit a binary 1, I can use I3. And I can change this over time. So over time, zeros and ones are represented by different impairments. So it's hard for an eavesdropper to adequately collect a large enough data set when this is also changing over time. And this makes it very differentiable. And as you can see, we have demonstrated this on different locations, both closed lab area and open recreational area. Each time, so here's the situation. If I simply take 16 X310 radios and if I collect IQ samples over a cable, I find that I can classify them almost accurately. I have 100% accuracy, right? So this is my baseline. This is over the cable. Now, what if I take this over the air at location 1? Again, perfect accuracy, because now I'm adding these impairments. What if I take this? What if I train on location 1 and test on location 2? I find, again, perfect accuracy because I'm introducing these distortions. Now, what if I don't do this impairment method? And this is the mess you see, about 35 to 36% accuracy, because the channel was affecting the classification. Now, these are 16x10 radios. Okay. Now, the take-away message is that impairments work. And to stress test this, we even adopted something, a different experimental environment where we are trying to classify UAVs. Now, we can inject the same impairments and in these transmitter 1, transmitter 2, and these are actually flying, and we collect these data sets, and we are trying to perform a classification and fuse the decision outcomes of all of these other friendly UAVs. And what you see is indeed this works. If you do the non-impairment method, you see a very low accuracy. You can see these low bars here. But if you do this impairment method, whether you do it in the air or in the ground, these are you have a very high degree of accuracy. So this is actually robust to strong fluctuations in the channel, hovering, motion, etc. And all these data sets, by the way, are available for you to use on my website. And let me know if you are unable to access them. You can always find them. Now, let me go ahead a little bit further on and tell you about a method where we don't inject the physical impairments, but we still distort the transmitter signals using an FIR filter. Now, an FIR filter is nothing other than a finite impulse response filter. It's what it is doing is this. Imagine that you have a filter tap, a series of taps shown by the FIR filter here. I'm going to represent the FIR filter using the term phi. Now, given an input sample, input signal, say X, this FIR filter is going to convolve with this input sample and is going to create an output. And this sort of represents the way in which a channel, a real wireless channel, distorts a transmitted signal. Okay. Now, why do we want the FIR filter to intentionally distort the transmitter side? We want to do this because, hey, look, you can compute these FIR filters, and you can process the effect of these FIR filters in hardware. They're extremely fast. If you know them, if you know the FIR filter that was used to distort, you can compensate almost perfectly at the receiver. So you can extract the original signal even if you distort it at the transmitter side, if you know what that phi is at the receiver, right? And so let's just see a little bit more about the pipeline as to how are we doing this. So our goal here is for the receiver to compute the optimal FIR filter that the transmitter is going to take and convolve with its own baseband transmitted signal. Okay, so let's say XA is going to be convolved with this FIR filter, and this is going to be done by the legitimate device, in this case A. Now, this convolved output is going to pass through the wireless channel. As you can see, the wireless channel is going to further introduce variations given by H, right? And plus, we're going to add a noise value to it, which is given by W. So I'm going to take the signal, convolve it with phi, and then again, the effect of the channel H plus the noise, and this is going to come at the receiver. Okay, so far so good, right? Now, what I'm going to do next is I'm going to take this received signals, and I'm going to pass it through my convolutional neural network to predict the device. And if I can do the device prediction correctly, I can identify the filter that was used to distort the signal. So I'm going to compensate for the distortion. And over time, because the wireless channel changes, I'm going to compute a new filter that I'm going to send back to the transmitter. So that's going to be the pipeline. And the goal here is to find this phi rather, in a fast enough way, in a meaningful way that is uniquely tuned to a transmitter, not just a random filter. It has to be uniquely tuned to a transmitter, because at the end you have to project its differentiating or its discriminating features in some space which is moving it away from the other radios, right? So for that you need a filter optimized to that particular transmitter's unique characteristics. All right, so let's just go through at a high level how we are trying to do this. Now assume that this is the baseband undistorted signal X, okay? And because of the filter action, you're going to have a filtered version, which is called this X hat, okay? Now this X hat is being passed into my deep learning CNN. And what you see at the output is a function f as a function f, which is nothing other than the probability of detecting the device given the distorted filtered signal X bar. Okay. Now what you see here is a gradient, and I'll come to the gradient in just a bit. But this is really f, which is the output probability that you want to maximize. And if you go a little bit deeper into this, and I'm just going to show you the output, the final layers of a classical CNN. Now, you have all these layers before, and this is the final layer that you can see here. The output of this is nothing other than a firing probability of a neuron, right? So this says that with a certain probability, this neuron is firing. So you say here that if you want to maximize this probability of this radio A, or this neuron that corresponds to this radio A to fire, you want to maximize this. Then, in other words, you want to maximize the firing probability over all the slices that you're going to feed to this whole neural architecture. And this is also a function of this phi, which is the filter that you're sending to the from the receiver to the transmitter, right? So now what I'm going to do here is that I'm just going to tell you a simple way as to how I am finding this FIR filter, right? That's going to be the main goal. Now, the way I'm using this is that if I use the CNN, I have a trained CNN. That means I can obtain the gradient of the output function f as part of the backpropagation path of the CNN. Now, if I go a little bit deeper into this, here is a path of the gradient, and the gradient is nothing other than, I can break this down as a function of phi as part of the Jacobian, and with an inner product of the gradient with respect to the distorted filtered slice. Now this I can easily get from Keras. This is the tool that is giving me this value. This I can compute. That means I can obtain this gradient directly as part of what I have as part of my trained CNN. So once I have this gradient, all I need to do is I need to find this phi. I need to pick a phi that pushes this gradient, that minimizes this error and moves along this gradient, right? So that is essentially how I'm doing it. And so in a short time, there's a lot of math behind it, which explains why this works. But this is the high-level intuition of this work. And if you do this right, you find that we are getting about anywhere from about 5 to 15% improvement over the previous results by using or the previous baseline, the raw baseline results, by using this FIR-based method. And indeed, if I know how much, if I know exactly which filter was used, I can compensate for this. As you can see, for these different distortion levels of the IQ samples, I can almost perfectly compensate for the action of the FIR filter. The question is, how does this affect this packet error rate? What is the effect on throughput because of these distortions? So as you can see here, that the packet error rate is less than 1% by careful selection of the epsilon of this distortion level, and the throughput is still, if you compare it with 0 and you compare it with these different levels of distortion, you find a very little reduction in the actual throughput of the transmissions. All right, so this was the FIR-based method. And the final piece that I want to talk to you about is a twist to the problem. Now, so far we said that, look, I'm going to give you a set of classes of radios, and you have to tell me which radio it is, okay? But here is a twist to the problem where I could also give you a new radio that you have not seen before, and you have to tell me that this is a new radio that I have not seen during my training set. So the intuition is as follows, as how we approach the problem. So let's say I have an in-library set of devices, and I'm going to train on all of them. And when I train on them, look at the way in which that testing accuracy is going to work. If I train them well, and if I give it, let's say, slices from this radio number 4, and this is testing time, I find that the radio number 4 has a pretty high accuracy at about 0.9 probability. Now, the others have quite a low probability, but the key thing to note is that no matter whether you give it slices from one of these radios or an unseen radio, you will always have a certain finite probability in this row. But the difference between a trained radio versus an untrained radio could be quite large. For example, if I give it a new device and if I pass it through the same architecture, I will still have one of the classes with the highest probability. But look at the difference between the classes now, what the difference between the maximum value now. And you find that this is substantially lower than the previous case where I had actually trained and tested on an in-library device. So this is the intuition that we're going to take. And the approach that you're going to, the contribution of this work is going to be, come up with a methodical way of setting these thresholds. Like, what is the threshold at which I'll say that this is far too much of a difference? So even though it is a maximum value of a probability, I'll say that it is an unseen device. So how do you come up with that threshold? And what statistical method will I use to create these decision metrics? So this is going to be my main sort of contribution towards detecting an outlier device. So you can see that an outlier, the detection of an outlier is often a fundamental step towards more complex parts. So we have extended this work further, in which we can also do lifelong learning, where we can. So in this work, I'm only going to say whether or not a new device is seen or unseen. But you can also do more, and you can say that this new device belongs to a new class, construct the new class, and then next time a new example comes in from the new class, say that this is a new class, right? So and differentiate among a number of new devices. So that's more recent work, but not covered in this presentation. But I'm going to talk to you about in or out library classification. So what we do here is we want to use the fact that the CNN has less certainty when you give it an input from an unseen class. So how do we make this decision, right? So we're going to basically take metrics and statistical thresholds that we see during training set, and we're going to compare these statistical observations in the test set. So this is how we work. We are going to take, remember that an example, I'm going to split this up into a number of slices. This goes way back into the initial way in which we are describing how the slices are done. So I take an example, multiple slices, each slice, and this is all during training, right? So each slice is fed into the classifier. Out comes a probability vector. I'm going to see, is the slice correctly classified? If no, I discard it. If yes, then I check the value of the probability. So is it 0.8? Is it 0.9? Is it much lower? So I take that value of the probability, and I collect these values for all the slices of the example. So imagine I have a long vector of, say, 0.9, 0.8, 0.9, 0.8, etc. That tells you the probability values only of the correctly classified slice. So I take that now, and I use some kind of a statistical function, and we have explored a number of them as to what is the right function that will best capture the performance. So we can take a number of these functions that we will use as to compute the final threshold. So, and I'll show you exactly which ones we have used. So the previous threshold was to say, what is the maximum probability? The next one is how many of the slices from a given example can be correctly classified. So this one, the intuition here is to collect a ratio of the correctly classified slice so that you don't have like a wild outlier, right? So for example, if you're able to classify, let's say 90% of the slices correctly, then you must see the same statistical observation in your test set. So that is really what we want to obtain, a ratio of the correctly classified slices. So we collect that ratio as well for each example of the training set. Now we have these two thresholds, again computed using these statistical methods, and we have a number of them. I'll show you in a bit how each of them perform. So we have a probability threshold and we have a ratio threshold. Now these are all obtained during training time. In the testing time, I do the same thing. I take my example and I compute these prediction probabilities and the ratios, and I then compare them. I then compare the two, and if what I observe is less than my probability threshold, and if my ratio threshold is less than the threshold ratio threshold, I say it's a new device. If not, then simply go and follow whatever is the output probability. So in this way, I can say with high levels of certainty whether or not an example is from an unknown device. So here is just a plot to show you that if I use statistical measures defined as LCB1, and I've shown you in the table what LCB1 means, or just the minimum value, I show you that how each of these choices so each of these points is a different statistical measure. So your goal is to sort of push this operating point to the far top right. So on a per example accuracy, we can do something about 80% times we can say that this is a new device that we have not seen before. But if we can use a multi-burst method, we can group them together. We can say with about 99% accuracy that this device is something I've seen earlier, and this is the device, or this device I haven't seen at all earlier, and this is a new device. And again, so this is a way in which we can do new device detection. Many ways to extend this into lifelong learning and so on. So finally, to conclude, I just want to say that that we have demonstrated that you can detect devices with 99% accuracy in many cases. There is a lot more other methods that we are using. For example, we have some recent publications on compressing these architectures using pruning and quantization, so that you can execute them, share these architectures in you can execute them in FPGAs and share them over the network without significant delays. There's a need to understand what is it that a neural network is really learning. And we are looking at information theoretic analysis to identify that, look, this is the contribution of the device. This is the contribution of the channel. This is the maximum performance that we can get when we have a mixture of these two and so on. So we need to understand a good theory behind it. And we always need better data sets and more applications of these. And so we have a number of data sets that we have released. I'm going to just give you an overview of what these data sets are. So I have a hat that I wear as part of the technical side of the Power Program Office. And so if you're interested in using the Power platforms, please go ahead and check these out. So these are real live data sets collected from the Power platform. We can do the same fingerprinting on 5G, Wi-Fi, and regular LTE waveforms. And this data set is also available on my website. We can also do a bunch of these for UAVs. In the previous example I showed you where we could inject a waveform, inject distortion. Now this particular work is on DJIs, where you don't even know what proprietary waveform they're using. So there's a number of interesting security applications of these, and you can easily see that this is a market that is going to explode. So with that, I am going to conclude my talk, and thank you very much for listening to me, and I'm happy to take questions. Thank you very much.
Thank you, Kaushik. It was wonderful talk, and thank you for the presentation. It was really nice. So at this point in time, we have some questions, and let's take the questions. So the first one is, thanks for the excellent talk. I would like to ask two questions. So we have two questions here. First, what could be the possible reasons for the performance degradation regarding training one day and test on another day? And the second question is, in practical applications, how to inject transmitter impairments or apply the FIR filter to the transmitter, as many IoT devices won't be able to be customized.
Well, you started the question answer session with the two toughest questions that that could be. Now, the wireless channel is really the problem, and we struggled with that problem for 2 years, and I don't think we have found a good enough answer as to how do we completely remove the channel effect. So look, we tried to learn the channel. We tried to do data augmentation to see more variances of the channel. What we haven't done is to augment it using channel models themselves, or our theoretical understanding of the channel models, where likely they're going to be used. So there is an opportunity there. We resorted to other methods as to using feedback to overcome the channel. But the bottom line is that if you want to really overcome the channel, I see that we would need some feedback, despite of all the tricks and the methods that we might use in the forward path. We will need some feedback on the reverse path. So that's something that will need to be done. Now, I think the FIR-based filter method is an easier implementation than actually distorting IQ samples. That has a more practical avenue towards deployment. I think the other question was that how do you do this when IoT devices are closed? And I completely agree that so this could be a problem, but if you remember that if there's a way, all you need is to simply modify the IQ samples in baseband using the FIR method before you pass it into the transmitter chain. So in a sense, you don't really need hardware access or driver access. You just need to distort the IQ samples in baseband before you send it in. So you still need some application, like a thin layer between the application and the lower, in the protocol stack before you go to the hardware. But yes, it's not going to be as bad as injecting an IQ sample inside it using a power amplifier gain or something.
I actually missed the first question. So the first question came from Jens Schlumberger. For the slide, learning the channel, how do you select the right part of a signal out of a bigger trace? How to classify preamble versus payload?
Right. So in this, well, we are assuming here that we can separate a preamble from a payload, right? So preamble is always going to be the first, 800, 1000 samples that you're going to get from any regular packet. So you don't need to know exactly the whole preamble and exactly take the preamble, because you're not doing decoding here. You only need to know that this is a piece of the overall packet that is always going to have the basic modulation scheme. So when you train on the preambles, you don't have to account for a number of different modulation schemes that your network architecture has to learn and compensate for when you estimate the channel. So it's not really so far as to extract an entire preamble, but it is extract the first few 100 samples, which are generally always the preamble of a packet. So that's one way in which we approach it. Now, once you know this, you can always split it. You can always split this a received packet and extract the first 100 samples. And that's what we have done. We have in the attention network piece that you see.
And I believe that most of the work is on Wi-Fi, so Wi-Fi preamble is known.
Right.
Right.
So Wi-Fi preamble is known. Absolutely, Wi-Fi preamble is known, and we have also done this on ADSB, which is for airline signaling, though we have not shown those results here. And I think we've also done this for LoRa. We have done this for yes, but so yeah, those are known preambles. But again, as I said, we don't need to really know exactly where the preamble stops. Just collect the first 100 or 200 samples. Generally, there'll be the preamble.
Sure. So the next question comes from Andrea Stomasi. I'd like to thank you for this talk, and I also would like to ask if the resilience of this system has been tested again an attacker that could jam the channel by injecting noise.
Right. So what we have done is, look, the problem is hard enough when there is no actual jamming. You know, the channel is changing, so it's the problem is hard enough. One thing what we have done from an adversarial point of view is we have tried to, for the FIR-based method, we have tried to say that what happens if an adversary were to obtain these FIR filters sent by the receiver to a certain transmitter, and then adopt them, could it influence the classification? So we have shown that no, it is not possible, because the FIR filter is computed as a function of the transmitter itself that was used at the time of training. So the way in which we compute the gradient is that we take the CNN, and of that particular transmitter itself, the signals generated by that particular transmitter itself is used to compute the gradient and the FIR filter. So it is somewhat keyed to the original transmitter's characteristics. And we've shown what happens if you take both of them at the same location, exactly on top of each other. Will it work? And we've shown it doesn't work. So we have done those kinds of studies of on the FIR-based method. But in general, yes, if you increase distortions in the channel, you will increase or you will decrease the classification performance. There's no doubt in that. That's certainly true.
Thank you. So the next question comes from Shen. Hello, Professor Kaushik. Could you please briefly introduce the purpose of training set normalization?
All right. The problem here is this, that you know, even when we start and stop the transmitter on and off, right, you'll still see a dramatic difference in the amplitudes of the IQ samples that you're receiving over time. And if you have that kind of an imbalance, your architecture is not going to learn well. So you must always try to balance the amplitude of these of a certain data set, as well as the diversity of conditions that the data set is going to see. So you should not see too many of one kind of class, right? So otherwise it becomes an imbalanced set. At the same time, it should not just see too much of extremely high values and too little of extremely low values, or vice versa. So for that reason, we normalize it. It just sort of makes a better training procedure.
So the next question comes from Laksima Kandal. Wonderful presentation, thank you. I'm wondering, how can we extract the IQ samples from off-the-shelf hardware? And I believe off-the-shelf meaning not the SDRs of the kind.
I agree with you. No, so far it's hard to do this. One thing what we have tried to do was there is Nextmon, which you can try, you can install it on Android phones, but you can only get up to CSI level information. Okay, you can get CSI samples, but not the IQ level sample. But I feel if you want to get there, that is probably the closest jump one can do. Engineer the the Nextmon to get to the IQ level, but I don't know personally of any off-the-shelf radio a commercial radio that you can, through API commands, collect IQ samples. So that's a bottleneck. So one thing what we can do is you don't do any. It's true. It's all of these methods were shown on SDRs because we could do that. It's hard to collect data sets, but if you want the data set, you can go to my website and get all the data sets you want at the IQ level. But no, hard to do this in off the shelf.
So the next question comes from Vijay Shah. Great presentation. How reliable would be the proposed approach to fingerprint 1.9 trillion devices? And how scalable and reliable would it be?
Oh, yes, yes. Well, if I had that, I would start a business and I would probably be sailing away on a sailboat somewhere at this moment. But here's my high-level answer to this. For DARPA, we were able to classify 10,000 Wi-Fi devices with 99% accuracy. Okay. Now, are you going to be in direct connection with 1.9 trillion devices as you move around in space? Likely not. You might have a restricted set of devices. I mean, probably no more than 100 or 200 devices at any one given moment in time. And that is an extremely small number. We can easily manage 100, 200 numbers, 100, 200 devices. Now, the only thing here is that we don't know which 100 or 200 devices they are. So if there's a way in which, as part of a signaling exchange, a handshake, you're able to, send over some sort of a device identifier or some sort of a classifier or sort of a key in which you can go download the classifier from a cloud, which is for that area, you can handle it. And that key can change as you travel, as you do for your DHCP address, right? So so you have different IP addresses as you move from one location to the other location. Perhaps you have a different classifier as you move from one location to another location. So you don't need to do all 1.9 trillion at one time.
So the next question comes again from Andrea Stomasi. Also, could an adaptive learning solution that tracks the changing of the channel without retraining the CNN be possible? Indeed,
for the FIR-based method, we are not retraining the CNN. For the FIR-based method, we have a trained CNN. We are going to keep it as is. We are simply going to take in the distorted or the filtered signal. The filtered signal has also the real life channel effect to it. And I'm going to use my gradient and that moment of time to compute the best FIR filter without retraining the CNN. I'm simply going to compute the gradient and use the gradient to determine the next FIR filter and send it back to the transmitter. So retraining is impossible in a live condition. The goal is how quickly can you find a good enough FIR filter as you're doing this gradient descent. And there lies a challenge, but it is still much faster than any retraining of the system. You're right, you can't retrain it in the live environment. So that's why we use the gradient to influence the peak of the next FIR filter.
So the next question comes from Manolaya Atalaya. Thank you for your great presentation. Have you ever considered comparing your works with attention-based LSTM networks or similar variants? Do you think multiple devices or agents would make this experiment inefficient?
So there are two parts to your question, right? So we tried LSTM, but it didn't work as well as we thought it should. And we also tried GANs for some reason, didn't work as well as we thought it should. So what I'm showing you here is a filtered output after many years of going away in rabbit holes. But that said, I want to come back and look at transformer networks and then look at the attention network again and see if we can do it better. So there is, I wouldn't say that's a done solution, that there's something to be explored there. So definitely transformer networks. And multiple devices agents is not at all inefficient because we are doing that for the UAVs. We are running this classifier at multiple locations and ground and in air. The goal here is to determine a weight for fusing and identify which one you're going to trust more. So we are using some sort of a CSI-based metric to allocate a larger weight for the final fusion from these multiple viewpoints. So it's good to have multiple devices and agents. Always great.
So the next question comes from C.T. Huang. Following the previous question, how do we know whether the normalization step is needed? Do you first see whether the learning is effective to determine whether normalization is necessary?
Well, as a rule, we always try to normalize, especially the RF input stream, just because even visually you can see the fluctuations. And for that reason, it's just too expensive. For example, a ResNet will take you 6 days to train fully, and you really don't have the time to even look at the validation set to see whether you should do it. So just take it as a step and go normalize it. It will not affect it. You're not definitely doing any harm in it.
So the next question that I was going to ask, but someone else asked, is, so this question comes from Jack Perazon. How hard would it be for an adversary to impersonate another device by adjusting their IQ imbalance or by using some other method? And my question was somewhat related to this as well, is how is it possible to listen to many of these transmissions and impersonate instead of knowing all the information?
Right. So you're right. So this is a problem of the IQ-based injection method. And this is also, I think you would have seen, the previous key exchanges that used to happen. If you listen long enough, they're all XORs at the end. You can determine the session key if you listen to enough of these in the past, right? So you're right. If you are able to hear long enough, then you will be able. It's essentially you're creating your own data set in that case, and then you will train a classifier using the data set. What we tried to do was to shuffle these arbitrarily over time and come up with some sort of a hopping sequence of zeros and ones, each zero being a certain impairment. But nothing to say that you can't break that. If you listen long enough, of course you can break that. You can. It's just going to make it a little bit harder because the impairment is switching itself. But the other method, the FIR-based method, is a lot more secure in that sense, because the FIR is computed based on the legitimate device's training set, and that as long as you don't have access to the training data, by simply overhearing, you cannot compute. You cannot. You will be unable to get the classification accuracy, even if you overhear the FIR filter, even if you sit on top of the legitimate device, so that in a channel sense, it is the same channel. So even if you do those two things, you're still missing the one last thing, where the CNN was not trained, or you don't have access to the training data used to train the CNN. So if you have access to the trained CNN, if you have access to you overhear the IQ samples, you also have the same channel as the transmitter. Yes, in all the three conditions, you'll be able to break it. But without that, at least we've shown that we haven't been able to break it, at least in the paper that we have out on this.
So the next question comes from Zushen Zhu. What's an amazing presentation? So yes, I agree with that. I would like to ask the question, in your paper, you mentioned low-cost devices are deployed in IoT network. So does the filter-based method cost more energy? Is that energy efficient?
So here's the thing, right? Even if you have an IoT device, you are doing a number of complicated processing steps to run a complete protocol on it. The filter-based method is simply taking, I think we have shown it using between 4 to 11 taps. It is simply taking it's a convolution step that you can do very fast in hardware, even in software, but also in hardware. So, and with that, you can easily do this without consuming more energy. So it's not at all an energy expensive method. The IQ impairment-based method is even less, because there's very little computation happening. There is simply one insertion where you're changing the gain. There is nothing else happening. So both of these are extremely low energy. What is energy heavy is the training time for training these on a large architecture like ResNet. But if you can do that in a cloud, then it's fine. What we've also done is we have shown you can compress something like ResNet down to about 20% of its total size, and by pruning weights, by quantizing weights, by which case you reduce the memory fingerprint, or the memory footprint, and you can really run it on very small IoT devices. So that is also one more step towards an IoT. But the FIR and the IQ, no, the processing itself won't take much time. The classifier, running the classifier could take time, but we have methods where we are done pruning and quantization. We have some recent papers in ICDM that show that how do you compress it.
So at this point, we don't have any more questions, but I have a couple of questions for you. So how is this technique different from physical unclonable functions that were actually inserted in hardware? And that has, and people are working in that domain as well. So how is is doing it with software and doing it with CNNs is different, or whether it's better or not?
Well, it's hard to say if something is better or not. The only thing I'll say is that so this problem has different incarnations, right? There is a version of this problem where we have shown this. You can do this using DJI drones, which you don't have access to the waveform itself. You don't have access to the hardware. You can only collect passive data sets and train on them. So those are situations where this approach will still be effective. Now, the more, I think the right answer to this is that if you don't know exactly what feature you are going to look for, if you want to minimize your hand engineering or expert involvement as much as possible, then some of these fingerprinting method and these deep learning architectures have an advantage. But if you want to make sure that it has to work no matter what, and you're willing to put in deep technical expertise on site, I would then say there's no need to go with this deep learning method. Let's go with the unclonable functions. So I think it's a question of how much technical expertise on site in the field and how much access to the device hardware or waveform, at least during training, that you're going to have access to. So that's where I think I would draw the difference.
Can you comment on the latency of the testing? So if, or in other words, how much time does it take to get the data from antenna and say that it is from this device?
Oh, I see. So, okay. So that I think we have, let me try and see. We have done this on, it depends upon what platform you're using. So for example, when we do something, when we run this on the NVIDIA GPUs that we have, we are able to do this in about few hundreds of milliseconds. Okay. Now this is only because of the pruning that we are doing on the architecture. Mm-hmm. If that is not, and again, it also depends upon how much pre-processing are you going to do, how much of filtering are you going to extract. So roughly look at the ballpark about few hundreds of milliseconds.
So basically the device has to wait for that long to get the next data going, or
no, it's just a streaming thing, but just a light will flash that says that at this point I can say with 99% accuracy that this is that device.
Okay.
So it can continue to stream in its regular data as usual, but just the decision metric will take a couple of 100 milliseconds.
Okay, that's wonderful. And I don't have any more questions from the audience. So before we leave, let's thank our speakers one more time.
Thanks, Kaushik. It was a great talk and great questions from the audience as well. Thank you. for coming.
Thank you. Thank you again, Dola. Thank you, Subha, for inviting me. It's always great having an exchange and great questions. I mean, this is really, I think, the best we can do in an online setting, and I really enjoyed it a lot. So thank you for having me.
Awesome. Thanks.
Thank you.
Bye, everyone.